that there.
That's fine, yeah. Right, and our next speaker is Thales Gutcke, presenting on streams.
Hi. Thanks for being here, or for having me here, and giving me a chance to talk about my work. I will not really be talking about the outflows that I said I was. I'm going to focus on the oxygen-6 in the halo of my simulations. So, yeah, I do cosmological hydrodynamical simulations with Andrea Macho, Aaron, and Greg. And yeah, the output of this work you can see on arXiv. So, to start, I work with a set of simulations called the NEHA galaxies. This is a couple of them. There's nearly 100 altogether. They were published last year. So for example, with this whole set of simulations that goes across over 4 orders of magnitude in halo masses, we can look at Mach optical images. We can also create Mach H1 images. And what's nice about these simulations is that they nicely follow the stellar mass halo mass relation pretty much across all of the orders of magnitude in halo mass. And you'll also be able to hear more about the NEHA simulations later today from Aaron. So what am I looking at using these simulations? I'm trying to compare our simulations with COS halos, mainly. So what is that? If you have a galaxy and a gas halo around it that's so faint that it's practically non-emitting for us, we can use a background quasar, take the quasar spectrum goes to the gas, and we can get the gas absorption in from the halo, and we can get it out to very high impact parameters away from the galaxy. So this is one way of probing very far away gas in the circumgalactic medium. And to compare those observations with our simulations, we have, so this is one galaxy forming also along a filament right here, and the color coding is by metallicity, and through the stellar, the star formation rate that we have, or the star formation in our galaxy, in our simulations, the stars form supernovas and create metals. So we track different abundances, and then the supernova explosions spread the metals throughout the CGM, and we can track this over time. Next, so I'm going to, as I said earlier, look at the oxygen-6 distribution. And to get the oxygen-6, I need to take the oxygen and get an ionization fraction. I do this using a cloudy model that I'll go into a little bit later. So then we can derive column density maps of oxygen-6 for all our different galaxies. This, again, is only a couple of them, not all of them. And based on the column density maps, we can then create Mach or stacked profiles of the different column densities. And this is the oxygen-6 column density on the left here as a function of the impact parameter. For our smallest galaxies here, low luminosity galaxies, medium luminosity galaxies, and a couple of our high luminosity galaxies. And then again, as a function of luminosity, in bins of impact parameter, so near to the galaxy, further out, and very far away. And sadly, unfortunately, similar to many other hydrodynamical simulations to date, we're not matching the observations as well, and that's why I'm talking about the oxygen-6 today, because I find that when simulations and observations don't match, that's where we learn things that we don't know yet. So one thing that's noticeable is that the simulations, which are the line here, with the 1 sigma scatter around it, is pretty much too low at all luminosities and at all radii. So to try and understand what we're doing wrong here, what we're assuming that might not be correct, we can look at how we're actually deriving the oxygen-6. So this is the phase diagram for 2 of our halos, a 10 to the 11 and a 10 to the 12 solar mass halo. The green contours here are the output of the cloudy model that gives us the fraction of oxygen that should be ionized in oxygen 6 at that phase. And the white contour is our gas distribution, the full gas distribution. Note that it's just contours, so of course, actually there's also gas further away from these contours. And then the background colors, the blue and the orange, are where in our simulations we're assuming that the gas is ionized into the state, oxygen 6 state. So for 10 to the 11 solar mass halos, where you can just kind of see it, the white dashed line here is our virial temperature for that halo. We're kind of creating a bimodal oxygen 6 distribution, whereas for larger halos with higher virial temperatures, we have just kind of one oxygen 6 region. And what's interesting is that we can, the cloudy model can be distinguished into the two channels that we're ionizing with. One is the collisional ionization, which is mainly based on the temperature and not so much on the density. And then the second channel for ionization is the photoionization, where we assume a constant UV background. And that's at much lower densities and lower temperatures. So if we split this up, yes, thank you.
And there's a question too.
Okay.
Is that mass weighted or volume weighted?
This is mass weighted. Right. So if we split this up and look at it as a function of halo mass, the fraction of oxygen 6 that is produced through the collisional ionization channel is nearly 0. So this is pretty much full photoionized, and this is fully collisionally ionized oxygen 6. And there's a nice sort of increase here where we can kind of create a break and say that pretty much the majority of gas in galaxies with high halo masses is collisionally ionized. In our simulation, this is just a prediction. I'm not trying to say anything about the observations yet. And then, yeah, so for our lower galaxies, it would be generally photoionized. And this is interesting in the cloudy model that we're using, where we're assuming collisional ionization equilibrium and photoionization equilibrium. It's not that surprising that there's a break point, because the virial temperature of the halo will increase, and then once you reach the collisional ionization region, you will definitely, it's kind of expected that you get a higher collisional fraction there. But definitely since we're looking for a reason or a way to increase our oxygen 6, one thing that, looking at this, we could definitely say is that maybe our collisional ionization equilibrium assumption is not correct. And there are many different non-equilibrium models out there, and they predict all different things. But one of them, from 2014, has a difference. So this is for oxygen 6. Look, you can look at the solid line, which is pretty much the prediction of oxygen 6 as a function of temperature, so the fraction, for the equilibrium model. And then in the non-equilibrium, in their specific non-equilibrium model, which is definitely initial condition dependent, you get this tail out to lower temperatures for a non-equilibrium model. And that, if you think back on the phase diagram, would definitely increase the amount of oxygen 6 being produced, especially in the lower mass halos. So that's pretty much it already. I wanted to keep it short and snappy. This is what you should take home from this. The oxygen 6 column density profiles are too low in many cosmological simulations. This is where we learn stuff, and there's multiple reasons. The one that I propose today is that the equilibrium assumptions in cloudy are too simple, but there's definitely also the question of how the stellar feedback produces the gas distribution in phase space, and that will surely strongly affect the distribution of oxygen 6. Of course, you can always look at the resolution power of hydrodynamical simulations and say that the hydrosolvers aren't good enough. Or what some groups have been looking into is other ionization channels than just a pure UV background in a collisional ionization. So for example, photoionization from the X-rays from stars in the galaxy, but that has been shown to pretty much only affect the very inner areas of the halo. That's it. Thank you.
Please.
You examined the possibility of ionization fraction, but I wonder whether it could be due to the metallicity itself is underpredicted in the first place. Can you address
Absolutely. So there's actually my next plot. So
I had the same question.
So this is the distribution of, so the one is the all metal or all gas in the halo and all gas in the disk, cut up by what metallicity they're in. So this is everything else. Here's the H1 fraction, then below is the oxygen, the metal fraction. And then of the metals, the blue is how much of the metals are in oxygen, and of the oxygen, the green is how much oxygen is in oxygen 6. And so looking at this, especially for the disk, I feel like, and this is a log plot as well, so this is very, very low oxygen 6 fractions, and I feel like, I don't know, this is just kind of a intuition or whatever, that we are producing enough oxygen, and it is, like there's enough oxygen even out to large radii, but that it's more an issue of the ionization into oxygen 6.
A new question maker.
Just a comment. There are many constraints, observational constraints of the oxygen column density in the solar neighborhood, so within the galaxies. Actually, within the galaxies, the column density of oxygen is very low. So that's could be another constraint for the feedback, for example.
Great.
Andre, one last one.
Thank you.
Have you compared low ions as well?
Have I, what?
Low ion absorbers.
Yeah, so I have H1 as well. Here we are. So this is the H1 maps, and this is the same plot I made for oxygen 6 earlier, but for H1. And this is not using a cloudy model for the ionization fraction, but using a fit to a radiative transfer calculation by Ramadi et al. And in this case, we're actually fitting the observations much better, except for very, very large distances. So out to at least the Vero radius, we're getting the H1 correct.
Very good. Let's